Hello and welcome. In this video we're going to take a look at and introduce the concept of a discrete dynamical system. So what is a discrete dynamical system? Well, it is one that changes as time passes. So for example, if you have a set of populations and they change over time, you have a dynamical system. The term discrete comes from the fact that we're only looking at discrete time steps. So essentially we're assuming nothing happens between two time steps, or that the process is not continuous. The processes that are continuous are often modeled in a class like differential equations. So let's take a look at an example and start to work around this and address what we might want to do with these dynamical systems. So here we have an example of one where people are going to move between one of two states. So we're going to assume there are two states here, and those states are urban living and rural living. So let's just imagine this is Coconino County, and we do some data analysis and we find out that 5% of people who live in the urban setting move to rural living, and 15% of rural living individuals move into an urban area. So we're assuming that nobody enters or leaves the county for now. In other words, that we're going to have a constant population. You can think of this as a closed system. And we will also assume, for simplicity, that we're dealing with only with 100 people. And this number is not particularly important. It just is a nice number that allows us to easily investigate what percentage of people live in each of these two regions. So we'll just assume that at time zero, that initially there are 20 rural dwellers and 80 urban dwellers. And ultimately what we want to determine is what's going to happen to these populations as time gets really large. So before we get into that, it'd be helpful to have some sort of way of diagramming this. Here there are only two states, but there could be more states, and thus we want to have some easy way of drawing it and representing it. So let me get my pen tool out here and let's pen out a diagram. So we said we have two states, and let's see here. Now, we need to come up with a system of linear equations that will allow us to calculate the number of urban and rural dwellers next year by knowing the number of urban and rural dwellers this year. So we're going to have actually four variables here. There's going to be u sub n, which is going to, and r sub n, which will represent the number of urban dwellers now and the number of rural dwellers now. And we're going to let u sub n plus 1 and r sub n plus 1 to indicate the number of urban and rural dwellers next year. So in this visualization, before we actually start using these symbols, we want to draw our state transition diagram. And this state transition diagram shows how people transition from one state to the next. We don't mean physical state like the state of Arizona. We mean two different possible situations that one can be in. So here's the rural state, here's the urban state, and we're told that 15% of those who live in the rural setting after 1 year will move into the urban setting, and 5% of people who live in the urban setting will move to the rural setting. Just indicated here that there were 20 rural individuals and 80 urban individuals at time zero. And then we need to ask ourselves, if this is going to be a closed system, meaning notice that there are no arrows pointing out, that nobody can leave and nobody can come in. And so if 15% of people who live in the rural setting leave the rural setting for urban, that means 85% stay. So we often draw this arrow back to, from the circle back to itself. And then if 5% of urban dwellers become rural dwellers, then that means 95% of urban dwellers remain urban dwellers after a year. If we wanted to use this data to, for example, calculate the number of rural dwellers next year, first of all, we would have to figure out how many of those rural dwellers remain. So 85% of the 20 people who live there now are going to remain rural dwellers, but so that necessarily means that the 15% will leave. We don't want to do things like have minus 15%. We want our percentages to reflect what number is present or what number will be gained each year. So we don't want any negative rates. We just want 0.85. So 85% of the 20 remain, 5% of the 80 transition over from urban to rural, and we could do the same thing for urban next year. We could say that 15% of the 20 rural dwellers become urban dwellers, and similarly 95% of the 80 urban dwellers remain urban dwellers, and so that comes out to 79. So we can build our little table here and show that at time 0, there are 20 rural dwellers and 80 urban dwellers. And notice that after each increment of time, these two numbers should add up to 100. So if we have that at time 1, now it's 1 year after we've started collecting our data, 21 rural individuals, 79 urban individuals. Now we could repeat this process, substituting in 21 for 20 and replacing 80 with 79, in both respects. So we see, one thing that we see is that the 20 and the 80 are common to both of these, and then this will help us build a system of equations. So we can again do that. The rural dwellers at time t equals 2. It's going to be 85% of the 21 who are present at time 1. And then they're going to gain 5% of the 79, so the new population in the rural setting is going to be 21.8, while that in the urban is 78.2. This may seem a bit counterintuitive because we see the higher rate of people moving from the rural to the urban setting, but this isn't the number of people, this is the percentage or the proportion of people. And so as this number gets bigger, 15% of a bigger number is going to be bigger, and as this number gets smaller, then 5% of 5% of that 80 is going to get smaller. So there might be some sort of stability in the behavior that we see. And once again, we should observe that there are 100 people present at time equal to 2. Now, to determine the number of dwellers after 5 years and 10 years, you can see how difficult this will be, because we're going to have to keep recomputing the new populations and then putting those in for the current Rn and Un plus 1. So you notice that this 21 is our Rn, and this is our Un, and here's the Rn and Un as well. And this is the Rn plus 1. That's the number of people living in the rural setting 1 year after t, 1 year after t equals 1. And this is the U sub n plus 1, the number of urban dwellers after 1 year. So there is actually a better way to do this, and that's going to involve working with matrices. So let's go ahead and develop that next. Okay, so the first thing we assumed was that we know the number of rural dwellers at time n plus 1, okay, so next year, is based upon, let's see what we did here. We took 85% of the number of rural dwellers this year. Okay, so that's going to be R sub n. Okay, whoops. Okay, and then we added to that 5% of the number of urban dwellers this year. So we'll call that U sub n. And then to get the number of urban dwellers next year, we said that that's going to be 15% of the number of rural dwellers this year, plus 95% of the urban dwellers this year. And we can see here the reason we wrote the number of rural dwellers first is because what we have is something that we can convert into a matrix equation. So if I turn this guy into a vector here, and I say this vector contains R sub n plus 1, and U sub n plus 1. Over here I can break this out into a matrix consisting of the transition coefficients, so 0.85, 0.05, 0.15, 0.95, and then the vector that I would kind of lift up. We can see that both of these equations contain Rn and Un, so that vector that's going to get lifted up is going to be Rn and Un. Now we could have switched these two equations around, but then we would want to switch the terms around here because we would hate to have a vector that requires an input of Rn and Un, but that outputs Un plus 1 and then Rn plus 1. So we just want to make sure that whatever order they get inputted into this vector is the same order they get outputted. Now we should be able to do the math on this, and we should be able to check that if I put in, for example, 0.85, 0.05, 0.15, and 0.95, and I multiply that by 20 and 80, then the output should be exactly what we got by doing it by hand, which was 21 and 79. So that should work out just the same, but notice that we don't have to do as much arithmetic anymore. This is a lot more powerful. We could just insert a matrix into our calculator, input the initial vector, and get the output vector that way. But now in order to get the time 2 state, we would have to replace the 2080 vector in our calculator with a 2179, and we could proceed in that way to get the time 2 state. So this was for time 1. This is going to be for time 2. And again, if I do 0.85, 0.05, 0.15, and 0.95 times this is going to give me my 21 point, I think we had 21.8 and 78.2. And the question we might immediately have is, can we do this faster? Is it possible to do this in a better way? Well, let's think about what takes place to get our next state from our current state. So in order to get the time 1 value, we had to take our 0.85, 0.05, 0.15, 0.95 matrix and multiply that by our current state, which was 20 and 80 for the number of rural and the number of urban. But that gave me the values at time equal to 1, right? That's going to be the 2179 vector. Now, what I want to do to that to get the time 2 state, this is time 1. This over here, remember, this is the time 0 state. To get the time 2 state, I've got to take the time 1 state and again multiply that by 0.85, 0.05, 0.15, 0.95. This is called the transition matrix. This contains the transition rates. This is the transition matrix. And what I see here is that I know that matrix multiplication has the associative property. I can't rearrange, I can't move this vector somewhere else, but what I can do is I can multiply these two matrices before I multiply that into the vector. So if I think about this matrix here as A times X naught, then A times X naught, well, by definition of powers, is equal to A squared times X naught. Now, unfortunately, when we multiply matrices, we don't multiply components across, so A squared is not a matter of just squaring the individual values. It means multiplying A by itself. And you can probably imagine that if I wanted to know, so this will give me my X sub 2, what we'll call X sub 2, which is the states at time 2. In the next video, we'll generalize this for what it should be at any given time, and then we'll proceed to figure out the steady state.